Transformations of functions, part 2. In last lesson, you looked at how you shift functions left and right and up and down by adding or subtracting things inside the function or outside the function. In this lesson, we're going to look at what happens when we multiply inside the function or outside the function. And this time we're going to start with outside. So we have our function x and f of x, which is shown on our graph, and we have 3 points that we are going to focus on, which are -3, -2, 0, 2, and 3, -2. So these points are the ones that we're going to look at and see what happens when we multiply the outside of our function. Now remember that the outside is essentially f of x is just saying the same thing as y. So when I say 2f of x, that means multiply 2 times whatever y value you've got. So in this case, it would be -2 times 2 is going to be -4. 2 times 2 is 4, and -2 times 2 is -4. And now I have the points -3, -4, so -3, -4, 0, 4, and 3, -4, 3, -4. And if I connect those points as best I can, maybe take out a ruler, that would be helpful, you get a new function that looks like this. And what in the world has happened here is we've taken our original function and we have stretched it. We have stretched it away from the x-axis. So this point stretched upward, this point stretched downward. So it's not a shift because not all my points moved the same. But my first point, it moved again away from the x-axis. This one also moved away from the x-axis to stretch my function. So here I've got, again, here's an example of a transformer that is ready to stretch. So what I did is I took him and I just stretched the function big. So this would be like my normal function, and I took it and I stretched it out, just in the y direction. X exactly stays the same. X stays the same in both cases. In this case, again, my function still goes from -3 to 3, but my y values have stretched. Okay, let's take a look at another example. What happens if I multiply by a number less than 1, by a decimal? In this case, 2 is greater than 1, and it's going to do something different when I've got a number less than 1. So if I again multiply my y values by 0.5, so I've got -2 times 1/2, or -2 times 0.5 is -1. 2 times 1/2 is just 1, and -2 times 1/2 again is -1. So now I've got the point -3, -1. 0, 1, and 3, -1. So if I take those, connect them up, what I got is a new function that has been compressed, that has been squished towards the x-axis. So we're going, in this case, squishing everything downwards in towards the x-axis. So a number less than 1, in this case 0.5, squishes my function in. It's called a vertical compression. If I have a number greater than 1, I have a vertical stretch. So vertical stretch or vertical compression. I think in your notes this word is a shift. You need to erase that, cross it out, and put in vertical stretch. That was what it actually should say. So vertical stretch is multiplying by a number greater than 1 outside my function, multiplying my y values by a number greater than 1. So pause the video if you need a moment to write that down. That's a vertical stretch, number greater than 1, and a vertical compression is, again, multiply outside the function by a number, I'm going to say actually greater than 0, but less than 1. And the reason for that is I want to make sure I'm not thinking about negatives quite yet. We're going to look later at what happens when my number that I'm multiplying outside is negative, but we're thinking right now just about positive numbers, +2, +1/2. So any number between 0 and 1 is going to be a vertical compression by that number. So that's what happens when we multiply outside our function. What happens when we multiply inside our function? For this one, we're going to take a look at some Desmos. We're going to use Desmos to help us, and we're going to compare the graphs and tables of these two functions. So you don't need to copy this part down unless you want to do a quick sketch of the graph maybe. We're going to do absolute value of x, which is your basic function. You know how that one works. And this should be, f of x f of x equals 4x, and this one's going to be f of x equals 1/4 x absolute value. So we're going to take a look at these separately. So first we're going to look at the table and the graph of absolute value of x and absolute value of 4x. So here we go. So here I've got the graph of absolute value of x, that's the one in red, and I've got the graph of absolute value of 4x, that's the one in green. So pause your video for a minute and take a minute to think about what happened to the red graph to produce the green graph. And if you can think of it in terms of horizontal direction, that will be helpful in this case. Okay, so you notice that each of these red points was squished inward, compressed towards the y-axis. You would be correct. So this point that was at 1, 1 has been compressed over to be just at, this is going to be 1/4 1. And this point that was at 2, 2 has been compressed to be at 1/2 2. That's 1/4 the distance. And the same thing has happened to these points on the left-hand side as well. The red was the original, and they got compressed inward towards the graph to get me my green graph. And you can see that with your table of values here. If you go, okay, -2 times 1/4 is 1/2, -1 times 1/4, -1/4, 0 times 1/4, still 0, 1 times 1/4, 1/4. So this 4 essentially has the opposite effect of what you would expect. You would think it would expand your graph outward times 4. What it actually means is it's going to take 1/4 the x distance to get to the same y value. 1/4 the x distance to get to the same y value. So just like yesterday's horizontal shifts were a little bit opposite, a little bit backwards, our compressions and expansions in the horizontal direction are also going to be a bit opposite, a bit backwards. So what happens when we multiply by 4? We actually get a horizontal compression by 1/4. Okay, so it's 4. Think of it as a fraction of 4/1. Flip it over, we get a horizontal compression by 1/4. Everything gets squished in towards the y-axis. In contrast, let's take a look at the graph of absolute value of x and the graph of 1/4 x. Maybe you can guess, even before seeing the graphs, what's going to happen here. So again, you can see their graphs and the table of values. Take a minute to think about what in the world happened when I added this 1/4 in. You may be noticing that instead of going over 1, up 1, I now have to go over 4 to get to the same y value. So I'm going 4 times as far in the x direction to get to the same height on the y-axis. And that's true. Over 2 up 2 is now going to be 4 times over 8 up 2 to get to the same y value. So this is now being stretched. It's a horizontal stretch by 4. So what happens when we multiply it by 1/4 inside? We have a horizontal stretch by 4. Again, flip over the 1/4. It does the opposite of what you think it should do. So we would normally think a number greater than 1 should be a stretch, but it's a compression. A number less than 1 should be a compression, but it's actually a stretch. Horizontal is backwards. You might want to take a minute and sketch these graphs in here so you have a reference, or just make sure you know how to do this in Desmos if you wanted to be able to compare later on. So in general, what are we looking at? Can we draw some general conclusions? Do we have some things in common? So anything that happens outside my function, that might be like an a times my f of x, or a plus h outside my function. Again, anything outside is going to be vertical. So outside is vertical. Both of these things, multiplying or adding and subtracting, is going to be a vertical something. Anything inside, so like f of b times x, and or x plus, or sorry, minus k, both of those things are going to be horizontal. And the other thing that's kind of strange about everything that's inside is it's opposite of what you would expect. So horizontal and opposite. In the case of the adding and subtracting, the plus goes left and the minus goes right. In the case of a multiplying, a number greater than 1 is a compression, and a number less than 1 is an expansion. So inside, horizontal and opposite, outside, vertical. We also have commonalities going in the other direction. Adding and subtracting a value is always going to be a shift. So horizontal shift, vertical shift, and it's going to be, in the case of vertical, up or down. And in the case of horizontal, it's left or right. Okay, so shift up or down, shift left or right, and again, it's the opposite of what you would expect. Positive goes left, negative goes right. In the case of multiplying, again, we have a commonality. This is going to be a vertical stretch or compression. And a horizontal is going to still be a stretch or compression, but it's the opposite of what you think. So vertical stretch is a number greater than 1, and a vertical compression is a number between 0 and 1. In the case of a stretch for horizontal, we're looking at a number, I'm going to call this B in this case, less than 1, and your compression is your number greater than 1. And just kind of for the completeness, up is positive, down is negative, but in this case, left is positive, right is negative. So you don't really have to memorize things if you can remember, or you don't have to memorize each of these individual cases if you can remember their commonalities. If you can remember, outside is always vertical, inside is always horizontal and opposite, adding and subtracting is always shifting, and multiplying is always a stretch or compression. So let's see how this applies as we keep going in this lesson. Keep this in mind. Here we go. One more thing to add to our knowledge is what happens when we multiply by a negative number. So again, remember that f of x is just like saying y. So negative f of x means multiply a negative or make all your y values change the sign. So a negative 2 is going to end up being a positive 2. A 2 is going to end up being a negative 2, positive 2. And what happens to this guy? Well, we have the point now negative 3, 2. We have the point 0, negative 2. And we have the point 3, 2. Take out my ruler, connect those dots. And what I've got is a reflection, a vertical reflection in the x-axis. So any points above the x-axis, they flip down underneath. Any points below the x-axis, they flipped up. So points above, flip down, points below, flip up. Any points on the x-axis, they just stay exactly where they are. And we have this nice vertical symmetry. So this is what happens? We get a vertical reflection about the x-axis. Anything above goes below, anything below goes above. So with that in mind, that will actually let us sketch some graphs that we don't know the formulas for. So if we want to sketch the graph of g of x, that's g of x equals negative f of x, I'm going to put in here, here's my x-axis is going to be my line of symmetry. And I'm going to pick a few key points to do a reflection of. So maybe the vertex seems like a good point to flip. Where else? Well, it looks like we've got 1 over 1 up from there. That's probably sufficient. So again, any point above, this is 2 above, is going to flip to below. This one, 1 over, this is 3 above, so this is going to be 3 below. 1 over 3 above, 1 over 3 below, and we're going to connect this to make it look like a nice parabola. And again, you should see that nice symmetry across the x-axis. Flip up, flip down, flip up, flip down, and we're good to go. One more. Maybe you want to pause the video, try this one on your own, and then come back and see how it went. Drawing your line of symmetry along the x-axis, pick some points, and reflect them. Okay, so this point that is 2 below the x-axis is going to flip up to be 2 above. This point that is 1 below flips up 1 above. This point that is 3 below flips up. And hopefully you can see your cubic forming It's kind of helpful to also remember that anything on the x-axis is going to stay there, so if we can get it to cross right there at the x-axis, then I'm good to go. Okay, what else can we do with these transformations? Well, given a function, we can describe all the transformations that have happened to the function. So looking at this function, I've got some multiplication going on, I've got some subtraction going on. So I'm going to actually just start with the subtraction because those are what we worked with yesterday. So I've got this -4 going on. It's inside my function, inside my cubic. Remember, this is your basic function of f of x equals x cubed. So inside I've got this -4. So inside must be horizontal. And it's going to be adding, subtracting, so it must be a shift. And it's going negative, so that must be to the right. Whoops, almost wrote left. To the right 4. So that's this first thing that I'm looking at. I'm going to do the other subtraction next. So -3, this is outside, must be vertical. Still subtraction, so I'm still looking at a shift. And I know that a negative vertical means down 3. And last but not least, I'm going to deal with this multiplication outside. Actually, there's two things going on here because I know there's negative. Well, I know the negative right away is going to be a vertical reflection. And the 2, since it's still multiplied, still outside is still going to be vertical. We got a lot of vertical going on. Vertical greater than 1, so this is going to be a stretch, a vertical stretch by 2. Okay, so those 3 things we got going on in this first example. See if you can pause your video and do example number 2 and then come back and check how you did. Okay, so we got going on here a subtraction inside my absolute value. So this is going to be inside is horizontal, shift, subtraction, shift. It's going to go right because it's negative, right 2. And then I've got handily on the outside as well an addition. So this is going to be now vertical, shift, up 1, it's positive. And then multiplying inside my function, I've got this 3, but it's still inside the absolute values. So this is going to be inside is going to be horizontal. Remember that horizontal is opposite, so bigger than 1, I would expect it to be a stretch, but it's actually a compression, a squish. And also remember that for horizontal, I need to flip the fraction. So if this is 3, it would end up being a 1/3 to squish it down to 1/3. Okay, so that's what I'm looking at. Well, let's keep going. All right, let's see what else we can do with these transformations. Write g of x in terms of f of x after performing the given transformation of the graph f of x. So what we're shown here, this half circle that we're looking at, is the function f of x. And we want to do these transformations to the function graph and then write g of x, what the equation would look like. So let's see if we can first do the transformations to the graph. A vertical stretch of -2. So this means we're going to take each of our y values and multiply by -2. And then a horizontal shift left 2. So we're going to take the result of that first vertical stretch and shift everything left 2. So take your y values, multiply them by -2. I'm going to choose these 3 points to work with. So you can kind of see what's going on. So vertical stretch of -2. Well, the y value here is -2. Sorry, 0 times -2 is still going to be 0. This isn't going to move at all for the vertical stretch part. A horizontal shift of, then the y value here is 3. 3 times -2 is going to be -6, so it flips over, which is what we would expect, and then stretches down. So the flip is the negative, and then a stretch, it's going to stretch away from the x-axis. And this one is still 0, so this would give me some kind of a stretched half circle. Not sure I'll be able to do it justice, but something like this, stretched half circle. Something like that. Okay, and after that, we're going to do our horizontal shift left 2. So take each of those new points and move them left 2. So -3 is going to be at -5. 0 is going to be at -2. Whoops, not moving that one, moving this one. 0 is going to be at -2. And 3 is going to be at 1. And then this would be our new function g of x. So as best you can, sketch it in stretched half circle. Okay, so that is what this would be, g of x. So that is what I'm looking at for the graph. Now let's see if I can write the equation. So I've got g of x equals, and then I want to include both the vertical stretch, so that's going to be a multiplication outside the function. So -2 times my function f. And then I know the horizontal shift left 2 is going to be inside. So I'm going to make that inside now. Left 2 is going to be x plus 2. And that would give me my new equation for g of x based on my original graph of f of x. So why don't you go ahead and pause your video now and try out example number 4, and then come back and see how you did. All right, so this is more or less what we end up with. Vertical shift of -3 moved everything down 3, and it's this -3 outside the function. And a horizontal compression of 1/3 means take all your x values and multiply them by 1/3. So 3 times a third is 1, -3 times a third, -1, 0 times a third, still 0. And that compresses everything in towards the y-axis. And again, it is inside, and it's the opposite of 1/3. Flip it over would be 3. Let's keep going. All right, last examples. Directions. Write a function, g of x, that is a transformation of the parent function. I think in your notes it says translation, but translation would be only shifting. Transformation means we're also going to have some stretches and compressions and maybe some flips. So we want to say first, okay, it says transformation of the parent function. So what would I expect in this case to be the parent function of my new function? Well, this looks to me like a cubic, like y equals x cubed, or f of x equals x cubed. Remember that the basic points for that, I have x and y table. If I had -1, -1 cubed is still -1, 0 is 0. 1 is 1, so my basic points would be here. And you can kind of sketch in, this would be my original parent function. So I've got to ask myself then, what happened to this parent function to get me this black function? Well, a few things have happened. The easiest to identify is just the fact that it's shifted over. So this middle point has shifted to this point here, 3 to the right. So I'm just going to write that shift 3 right. I'm going to need to include that in my final equation. If that was all that happened, then this point would be here, and this point would be here. So it's not the only thing that's happened. It looks like my function has also been stretched vertically. That this point, which used to be 1 away from the axis, has been stretched up to be 2 away. And this point that was also 1 away, 1 down, has been stretched up to be 2 down. Now, you could, if you wanted to, also think of this in terms of a horizontal. You could say, well, actually, this one has been pulled inward, this one has been pulled inward, but it's a lot harder to tell exactly how far in this has been pulled. So vertical shifting, or vertical stretching and compressing is going to be easier, just in general. So always look for that first, unless you think you can find the horizontal pretty easy. So what this has done then is this has taken a value of 1 and multiplied it by 2. A value of -1 multiplied by 2. And this one at 0 stayed there. So what I have then is a vertical stretch by 2. Vertical stretch by 2. So I've got these two things going on, and I think that would be enough to get me straight to this new function. So if I want to write this as an equation using my parent function, so I've got doing g of x is equal to, okay, shifting right, that's going to be horizontal, that's going to be inside, and vertical stretch, that's going to be outside. So outside, I'm going to multiply my function 2 times, and inside, I've got to shift right 3, so that's x minus 3. If you're not 100% sure that that works, go ahead and pull out Desmos and type it in and see if it gets you the points that you would expect. This 4, 2, and 2, -2, and the right. All right, let's take a look. So the parent function of this last example is y equals absolute value of x. And actually, you could have done this one based on what we know from our absolute value unit instead of using transformation. So that should hopefully reassure you if you got an answer that fits with what you would know from our absolute value unit. So let's think about what's happened to this function. One of the things that may be the most obvious is that it's been flipped upside down. So it should involve a negative. It has a vertical reflection. I'm going to start using different colors, see if I can get this. So I've got a vertical reflection to make it point downward. Or in the case of thinking absolute value function, we flip it over so that what was a positive slope becomes a negative slope. You know, it's opening downward, it's got to have a negative slope. So we've got a vertical reflection, and then you can tell that it's been translated, let's see, 1 unit to the right, and 1, 2, 3, 4 units up. So if I just did that part, that would get me at least my vertex in the right place, but it would still end me up with a slope of 1/1. There we go. So that is with our shift right 1 up 4. And then last but not least, I would have to change the slope of my lines, or think, okay, what happened to each of my points so that they ended up on the right spot? How do I change the slope? Well, that's going to be a vertical expansion or compression, vertical stretch, or vertical or horizontal. If you wanted to do horizontal, in this case, you might actually be able to figure it out. So I'm going to call this, in this case, a vertical. And I think it is going to be a stretch. It's going to be a number greater than 1 because I end up being a steeper slope. And this point here that was 1/1 down is now 1/1, 2, 3 down. 1/1, 2, 3 down. So I think that's going to be a vertical stretch of 3. So if I put those all together, hopefully to get my final answer, I've got then g of x equals, let's see, vertical reflection and vertical stretch, those are going to come in front as a -3. Absolute value. Between these two, the right one is going to be inside, so this is going to be x minus 1, absolute value. And then my up 4 plus 4 comes at the end. Now, you may have noticed that when we did the vertical reflection, it did flip over the x-axis. But then once we shifted it up, it's no longer flipping exactly over the x-axis. If we had drawn it before flipping, it would have looked something like this. And what ended up happening if you do the flip later on is it just flips right over its vertex. So kind of a little bit interesting. You can play around with Desmos to see how different transformations work in different orders. All right, that's it for this lesson. Good luck with your homework.